Good afternoon. It's really exciting to see so many great use cases and the growth of this community. I'm Yunpeng, Ritwik. We're from Zoox. We're building Zoox autotuning systems. And this talk will be divided into two parts. First, I will talk a little bit about the Zoox and the unique challenges we face when scaling self-driving algorithm development, and how Ray integrates into the Zoox ecosystem. And following that, Ritwik will be elaborating how we leverage Ray's capabilities to scale our workload. Okay, so this is our robot taxi. If you were to spend just 1 hour on the street of San Francisco, it's very likely that you will come across one or multiple fully autonomous vehicles. You might have spotted some of the Zoox testing vehicles, but you probably haven't seen this. This is our robot taxi. But if you spend some time in Foster City, or more recently in Las Vegas, especially around our headquarters, you will see our purpose-built robot taxi operating on public streets. There is no steering wheel because the vehicle was designed for passengers, not drivers. Our vision is providing mobility as a service in dense urban environments. In order to achieve that vision, we have to address a few core challenges. One of the challenges is scaling algorithm development to a diverse driving scenarios. Now let's take a look at a simple example. Let's consider a typical driving scenario. You are driving straight, and there is a vehicle in front, and there are two vehicles in the adjacent lane. What is your move in this situation? Well, it depends on a combination of factors, including your immediate objective and your predictions about the behaviors of other vehicles. You can choose to drive straight and just follow the lead vehicle. Or if you are looking to accelerate, you can switch to the adjacent lane and follow the lead vehicle there. Or if you're really in a hurry, you can even change lanes once more and return to your original lane. Now, which of these options is the best? The planning algorithm at Zoox is quite intricate. Fundamentally, it is based on minimizing costs. This cost can take various forms. But for simplicity, let's consider three: safety, comfort, and progress. Our goal is to select the plan with the lowest overall cost. We take into account things like the uncertainty of the world and the hierarchy of the cost types. For this discussion, let's focus on a basic linear combination of these three costs. The challenge lies in determining the value of these weight parameters. They don't have a direct physical interpretation, and heuristic rules don't scale very well. Guessing them is not a viable solution. Our goal is to tune them to improve overall driving performance and ensure scalability across a wide range of driving scenarios. One common practice is to tune them by hand or manual tuning. We can choose a driving scenario, select candidate parameters, run simulation, analyze simulated behaviors, and refine the parameter iteratively until we are happy with the tuned behavior. However, manual tuning can be a cumbersome process, especially when dealing with the numerous parameters and the wide range of driving scenarios. This approach significantly increases development time, and it could become a never-ending cycle for developers. Our goal is to achieve parameter tuning that is scalable across a wide array of driving scenarios, all without increasing the engineering effort for developers. This approach not only saves a lot of trial and error time, but also allows our developers to focus on refining the core algorithms. Our strategy is closing the loop and automating the entire process. Instead of manually observing simulation results, we execute simulations across a wide spectrum of driving scenarios, collect relevant metrics, and utilize these metrics as criteria for optimizing the parameters. One of the challenges is simulation and metrics computation of many scenarios within a limited time frame because we have limited compute resources. Given the iterative nature of the parameter optimization process, we need to simulate the same set of scenarios hundreds of times with different parameters, leading to millions of simulations within this tuning loop. We will cover how to scale this workload in the later portion of this talk. To illustrate, let's consider one instance of an end-to-end autotuning run. We use 6,000 training scenarios, and the process takes 200 iterations and approximately 30 hours on an 800-node cluster to complete. Because we simulate the 6,000 scenarios 200 times in the optimization loop, so the total number of simulated scenarios is more than 1 million. By using this approach, we have achieved a 20% boost in safety metrics, a 30% improvement in comfort metrics, and a 5x improvement in cost efficiency. It is worth noting that the improvement in cost efficiency is the direct result of our integration of Ray and the infrastructure we have built around it, which will be covered in more details later on. This video provides insights into the diverse range of scenarios we use for training, including some edge cases and some common situations we usually encounter in cities such as San Francisco. For example, double-parked cars. We must account for all of these scenarios in our training data set to achieve scalability. And we need to ensure these scenarios are well distributed in our training set. Before we transition to the second part of this talk, I'd like to give a brief overview of our platform. It is fully configurable, allowing developers to select dataset labels for training or validation, specify parameters for tuning, and define objective and constraint metrics. Results can be tracked using internal tools or external platforms such as Wisdom Biases and MLflow. Ray and Raytune play pivotal roles as our orchestration layer. And Ritwik will be explaining how we leverage Ray's capabilities to scale our workload. Oops.
Hopefully this is working and everyone can hear me fine. Okay, cool. Thank you, Yunpeng. Yeah, so as just mentioned, to enable auto-tuning of parameters for this driving stack, we need a fast turnaround time between iterations. So in this segment, I'll basically go over how having a Ray-backed platform gives you that fast turnaround time and how you can do that repeatedly in a reliable manner. First, we'll talk about resource-aware execution. It's just a phrase a lot of you might think, what is this? So Ray scheduling allows us to maximize our resource utilization and use whatever is available. Our workloads are extremely heterogeneous. It's not just simulations. We do a lot of other computations with simulations. And that's where Ray's pipelining comes into the picture. So Our jobs at Zoox, and most of them being CI jobs, involve thousands of individual tasks. Each task involves our driving stack being tested in a simulated scenario and successfully evaluated for drive quality and performance. Like these simulation tasks often need like one CPU and one GPU to run, and then computing the behavior and running a bunch of other metrics computations, let's say, needs 2 CPUs to run. If we take the example of a single physical host, you have 2 scenarios. You can see that the simulation task of scenario 1 starts running first, and then as soon as it finishes, the GPU is freed, and it begins to simulate the next scenario. The scenario 1 simulation result is then offloaded onto the background CPUs that are available, and then metrics computation begins on those. So you're never wasting any amount of GPU time, and this is pretty critical because this is 2 scenarios, but when you scale this to 6,000, you save 20 minutes out of 1 hour, and when you have 100 jobs running every day, that amounts to lower AWS spends. But pipelining computation is just the start. We also have other force multipliers, more arrows in our quiver, so to speak, to increase the throughput of our simulation workloads. An example here shows us that we're being bound by GPU memory budgets. So because of the available GPU, let's say it's a 12 gig graphic card, and we have a simulation that needs 8 gigs of GPU memory to run, we can't fit more than 1 on it. So 4 gigs of GPU RAM is basically going to waste. But Ray allows us to use fractional resource specifications, which means that we can squeeze in multiple simulation tasks per device, depending on the available hardware capabilities. For example, if you had a beefier GPU, let's say a GPU with 16 gigs of RAM, you could then fit your 2 8-gig simulations on there. Or if you had access to some kind of custom memory allocator, like unified virtual memory from NVIDIA, that will allow you to augment your GPU RAM budget using your physical CPU RAM available. And then, using that managed memory allocation scheme, you can start to squeeze in 2 simulations per node. But it's not always about increasing throughput or just squeezing in more simulations. We have different kinds of execution pattern needs. In our CI jobs, we often need to measure if a pull request opened by a software engineer at Zoox is going to impact the latency, the software latency of our on-vehicle code. But measuring software latency is not super straightforward, especially when even a few milliseconds of variance here and there can impact the quality of code going in. A quick primer. CPUs are essentially divided into different nodes that have a bunch of processors and memory banks in them. When code runs on these processors, it can access memory present in a memory bank which is local to it, or even in a memory bank that is not local to it. When it goes the not-so-local approach, it adds a few milliseconds of latency. And when it does that, it becomes increasingly hard to determine if the regressed latency was due to a pull request opened by a software engineer, or whether it's just hardware-induced variance. So we want to avoid that. We want to minimize core contention, and we want to ensure that memory accesses are local. We use tooling like NUMA-CTL to basically mask out entire NUMA nodes from CPUs. So this ensures when code runs on a particular node, it utilizes processors and memory banks that are local to each other. In this example, you can see that only one NUMA node is visible to the Ray task for running, and then the latency measurements are as accurate as possible. Next, we're going to talk about dynamic cluster orchestration. Anytime a CI job is triggered, we spin up a new Ray cluster on the fly. Resources are provided by Slurm at Zoox. Essentially, when Slurm starts providing resources, we have a bunch of Docker containers that come online. Each Docker container has access to a unique job ID, which is linked to the CI job that triggers it. When the first node comes online, it registers itself as the head node, and in Redis, which is a key value store, it broadcasts its IP information using a setNX operation. When other nodes start coming online, they do a lookup at that same job ID key, and because of setNX, it essentially becomes a read operation for them. They read the head node's IP, connect to them, and the cluster upscales organically as time passes. We also try to ensure any kind of networking errors don't happen during startup, and we do that by avoiding any kind of race conditions. As I mentioned before, our nodes are essentially Docker containers spun up on physical Slurm hosts. If we start to instantiate 2 Ray nodes in these Docker containers, then what may happen that both of them find one free port at the same time, and while one of them will be able to successfully instantiate Ray services, the other one will see that it's no longer able to do so and lead to networking errors. So we avoid that by just spinning up 1 container per host. Also, our deployment is extremely flexible. All we need is a base OS installation and a GPU so we can run it anywhere on-prem or any kind of cloud service provider. At Zoox, we extensively use Bazel to pre-package all our software, including all our Ray software and any kind of user source code pre-built into binaries. And all of that is packaged up into tarballs that are fetched at runtime. You don't need any kind of custom AMIs, Docker images, none of that sort, no dedicated cluster. You can just run it on any computer. And because we utilize a general pool of compute for our nodes, we try to be extremely prudent in our usage. For example, if we don't have enough workload to fully subscribe our available compute, we return anything that is no longer needed. In this example, you'll see that the central node no longer has any Ray task left to run. We have an idling monitor that monitors for these metrics, and as soon as it finds such an idle node, via Slurm's S-cancel operation, it kills that node goes back to the general pool, and we use only what's needed. Finally, I want to talk about fault tolerance because, as anyone in this room would know, having a CI infrastructure means it needs to run reliably 24/7, 365. And things are not always perfect, so we need to know how we're resilient to external failures. External failures come in many forms. This is one example. You can see that there's a node with a bad GPU. It can either be a bad hardware problem or just an incorrectly configured CUDA installation. If our simulation tasks land on these bad nodes, then they could affect the results generated, and then they would skew the results of the overall CI job. To alleviate this, we run a series of health checks at the beginning of the Ray job to evict any kind of cluster, any kind of node that doesn't meet our hardware requirements in the cluster. In this case, the middle one is evicted. We tend to download a lot of assets at runtime. These include simulation assets like 3D mapping data, for example, to run our sims. These come from external resources like Artifactory. So if we detect that one of the node doesn't have a proper network connection and is unable to ping a host, it's evicted from the cluster. Also, many times things aren't really detectable right at the start of the job. Things start going wrong while the job is in progress. Our GPUs run millions of simulations day in and day out, and it's not unusual for them to enter into a bad GPU state, which will basically render them useless for running heavy simulations. We continuously poll them in background threads, and if a GPU enters in a bad state, these tasks that were bound for that bad GPU host, they're resubmitted, and the host with the bad GPU is evicted, just as it is in a downscaling operation. So all of this stuff is about the execution engine itself that provides a fast turnaround time for autotuning, and it's also something we use in CI. But how does it all come in the bigger picture? So when a software engineer at Zoox opens a pull request to validate their code, it triggers the build and launch stage in our build farm. Essentially, their source code is built from the branch using Bazel, and then all of that is pushed to an external build cache, which may be S3 or some kind of file system store. At the same time, we send a request to Slurm to start providing us compute resources, saying, hey, we're about to run a job, better start providing us resources. When Slurm does that, we have a bunch of physical hosts and Docker containers available. We start downloading our platform's software code, which is basically a tarball package. And all that user code that we built when the pull request was open, it gets downloaded onto each of these nodes. When this happens, we're finally ready to initiate our Ray services on each of these nodes, start up the Ray cluster, and then the job begins to run. When the job finishes running, all the results generated from the simulations and the metrics computation, they're streamed to external endpoints. We use streaming endpoints like Kafka, and we also have persistent stores for when we want to introspect our simulation results, maybe 30 days later. These may be S3 or some kind of file system store. In conclusion, with Ray, we've been able to build a very general purpose, large-scale workload runner that is flexible in its deployment methods. You can run it anywhere. You don't need any kind of custom infra support or installation. It's super elastic. Jobs start running as soon as they have just one node available, and they run multi-thousand node jobs pretty easily. Because of like fractional resource utilization, we're super efficient. We don't let any amount of GPU memory go to waste, and we try to use all available CPU cores. And like I showed in the latency example, sometimes we have these weird execution pattern needs, like constraining things to a CPU set. With this platform, we can do that. But we want to keep going on towards perfection, and there are still things to be worked on. Our in-house infra ecosystem and integration with things like GitHub Enterprise is still something we're working on for our array-backed jobs. We also perform a lot of baseline simulations when we validate pull requests at Zoox, which means we're repeating a lot of baseline compute, which could be avoided. We're looking at investigating options like Ray workflows to deduplicate such computations. And with that, that's the end of the talk. Thank you for listening to both of us. Yeah, regarding questions, we don't have mics, so you can just like say your question. I'll repeat it for everyone else, and then we'll do it that way. Okay, yeah. Yeah.
So you're running one cluster per simulation job, and these are huge simulations. You didn't talk about scheduling. I imagine that people schedule their simulations in some centralized scheduler that can allocate and figure out when a cluster becomes available, then, or rather when nodes become available, it can spin up the cluster and send the next one in the queue. How does that work?
Right. I think it's a great question. The question is, we spin up a new cluster for every job, and essentially, how do we define scheduling those resources to be available themselves to run that job? That part is entirely handled by Slurm. So we have a pre-packaged specification that each of these jobs are going to be, let's say, 200 node jobs for these 4XL instances. And then that scheduling is just essentially handled by a centralized Slurm scheduler, which provides those resources from that general pool. There is no context about if it's a Ray job or not at that level. And then the Ray portion kicks in once those resources are made available to us by Slurm. Yeah, I think this looks like that was just one.
Can I ask a follow-up?
Yeah, sure.
All right. So I imagine before you developed that, you probably considered just having a very large Q-Ray cluster that you would then not tear down from simulation to simulation, but instead run multiple simulations or all your simulations on that single large cluster. What's the reason that you opted for this approach rather than the monolithic gigantic cluster approach?
Yeah, it's a great question. Why didn't we go for like a dedicated Q-Ray kind of service, which would prevent us from having to set up and tear down a Ray cluster every time? I think the simplest answer there was like engineering cost. That would require support from like a lot of other teams, like and would require a lot of engineering man-hours to set up infrastructure like that. And with this, we could just reuse the existing HPC ecosystem that we already had at Zoox, and then from their point of view, it would just be a bunch of Python executables that are running there. So it was the lowest friction path that we had at that time. And it's been 1.5 years since we've been using the system, and it hasn't caused any major issues. So we're still sticking with it. Yeah.
I think another reason for that is that we support a lot of different types of workload. So we need to configure the cluster differently for different workloads. So that's why we're now taking this type of approach.
Okay. Thank you.
Yeah, that is a good question. So the matrix calculation, I think 100% of them are on CPU, not on GPU. Yeah. But we do multi-threading for the matrix calculation.
And that's like in the same like Ray cluster? Or
Exactly.
Yeah.
We only use CPU resource to calculate the metrics.
Why Slurm and not Kubernetes?
Great question. I think the answer of Slurm versus Kubernetes would be this, similar to one which I gave. Slurm is basically what powers the entire HPC ecosystem at Zoox and has already done so for like many, many, many years. And so that was just the easiest thing to go with instead of trying to build out a new resource provisioning mechanism. So yeah, that's basically it. Yeah.
How do you persist the logs back to the users after the job has been?
Yeah, so as I mentioned about results being streamed to like endpoints like S3 and Kafka, we also use file store for persisting logs. So we have networked file systems that are mounted to each of our physical nodes. So all those logs are written to those persistent locations. And then we have a lot of downstream post-processing that cross-references everything together. And so when a user sees it on a user interface, everything is still available. Yeah.
So, yeah, following up, it sounds like it's a scheduling cluster management rather than the typical array use case. I was wondering what's like the corresponding 1.5 years ago was the in-house crafted scheduling system being used.
Yeah, I think, so for us, Ray has been more of, Slurm has been a scheduler for scheduling at a more higher level, like physical compute resources, and Ray has been at a more atomic level in which we're trying to distribute scheduling of individual Python functions and routines. That is something that we didn't have an in-house solution for already. We had solutions for scheduling when to run certain executables in containers, and when to run certain commands in Docker. But the ability to like atomically decide when this particular Python routine is going to get triggered, or when it's going to run, or on what resources it's going to run, we didn't have like an in-house solution for that. And Ray was perfect because you basically just need to add a decorator to existing code, and then that's it. So it's a more atomic level scheduler for us. Yeah.
Does your build system also build the image that the Ray workers use, or do you use the image from Docker, from like Docker?
Yeah, so those images are basically very thin wrappers around the base Ubuntu images. We have integration with Bazel and everything, but they're built separately with no awareness of whether a Ray job will run on them or not. And they are the same images that are universally used throughout the company for all kinds of use cases. They're handled internally by our site reliability engineering team. And I believe, I mean, they'll be the best people to answer to this, but they use standard Dockerfile practices to prep those images. But they have no context about what job is going to run on them. So there's nothing pre-installed in those images for running Ray jobs.
So follow up about the images. So you mentioned that the developer code is packed up in like tarballs and then downloaded. So like you're reusing the same images job to job. Is that right?
Right.
It probably saves a lot of time. You don't have to like
Yeah.
Do you hold on to nodes like so you don't have to release them when the job ends? So like the next job can grab them. I guess maybe you didn't go into if it's like a local or a cloud.
Right. I think right now, because as a company, Zoox, we use reserved instances, but internally when those instances are at Zoox, once a Ray job finishes, they might go back to another Ray job, but we never hold them for 2 consecutive jobs. They go back to, okay, any other engineer at Zoox needs them for something.
Right, of course, but then like I guess the advantage is that node already has that image cached, so you don't have to.
Yeah, exactly. There's no re-download or reset.
And then that makes things pretty fast.
Right, yeah, the tear down is super quick.
Yeah.
Can you share like something about the debugging?
I think I will admit we don't have a perfect debugging solution for array jobs, but of late we've been trying to better use Ray dashboard for live introspection and saying that, oh, if you have some tasks failing, then what's the source of the failure? Are they located to a specific node? Is it because of a hardware failure on that node? So I think we've been trying to use Ray dashboard for like live debugging a lot whenever we see an alert regarding to when something's wrong. We also have kind of like hacky ways of seeing what's wrong. If we know that there's a problem in a container, we just log in, attach GDB to the Ray process or the running task and see where it's stuck at. So there's no principled solution that we've developed. It's just very ad hoc, but the dashboard has been super useful there.
With the dashboard, are you keeping up then after the jobs are done?
No, they get torn down.
Because normally I think like when I use the dashboard, if the cluster is gone, like I can't.
Yeah, it's only it's only for live. Yeah.
You mentioned about GPU fractionalization.
Mm-hmm.
Is it dependent on GPU or like they can do it?
Yeah, so that's something kind of triggered on our end. The fractional resource specification is calculated by us and then provided to Ray depending. We already know what type of hardware the job is going to run on. So for example, if we know that our sims take 8 gigabytes of memory and it's going to be a 16 gig GPU that is going to be available on the nodes in the cluster, then we send like, okay, num GPU is 0.5. But that calculation is predetermined, and it's predetermined based on factors determined by us. And it's all hard-coded. Ray obviously doesn't do that dynamically. So yeah, there's that. Okay, thank you.
Thanks.